So it wanted you to write the shifted or transformed function for y equals x squared if you shift right 7. So Cameron, you want to tell me what you and your group decided that would look like?
X minus 7 parentheses squared.
Excellent. X minus 7. I always say sometimes like quantity squared. When I say quantity, I mean parentheses. Excellent. I'm going to put a y equals in front, but that's fine. Andrew, what did you guys say for B?
I got y equals parentheses x plus 3 parentheses squared.
Excellent. Look at this with an eagle eye. Did you put your square on the outside of the parentheses? I've had a few people today, we're putting it on the inside, and we don't always catch that, but it should be on the outside. Let's see. Tate, what did you guys say for C? Like this? Yeah. And on this one, because you have only one term in there, do you really need the parentheses? No. So y equals x squared plus 4 is also fine. Excellent. And Kylie, will you tell us what you guys got for D?
Y equals x squared minus 6.
Excellent. So hopefully you remembered this from Algebra 2. When you're doing left and right shifts, they go inside the parentheses or inside the grouping symbols. I always told my students in Algebra 2, the H looks like the opposite of what it is. So when you want to go right, it looks like a minus. When you want to go left, it looks like a plus. And then K is on the outside when you're affecting the Y. It looks like what it really is. You add or subtract that value. Did any groups remember how to vertically stretch a graph? Raise your hand if you could vertically stretch. Josh, what did you put for vertical stretch?
F of x equals 2x squared.
F of x equals 2x squared. Okay, awesome. That is a vertical stretch. Can you give me another number that you could have used to vertically stretch? Besides 2?
Anything above that? Anything above 1?
Anything above 1. So we could do 3 or 4 or 10, right? That would be a vertical stretch. What would vertically shrink your graph?
Anything less than 1?
Anything less than 1.
And greater than 0.
And greater than 0 in absolute value. Yes. Okay. Let's see. Reflection in the x-axis. Oh, Logan, you want to do it? Okay.
Y equals negative x squared.
Y equals negative x squared. Excellent. So think about with reflections, if you had a point up in quadrant 1 and you reflected it in the x-axis, then it would land in quadrant 4, which what's the only difference in the coordinates from quadrant 1 to quadrant 4? The y coordinate would be negative now, right? So we're changing the sign of the y, but the x's really wouldn't change in that reflection. So if your y was x squared, we're just going to make it negative, and it is the function negative x squared. If you were reflecting in the y-axis, what will change? The x, so we would want to put that in parentheses. So we would do like negative x quantity squared. Well, negative x quantity squared is just x squared because it's even power, right? So would you agree if you took a parabola, the parent function, and you reflected it in the y-axis, it would just be itself, x squared? Good. So at the bottom of that paper, we're going to consider this part of your notes. Okay, so this is going to give us the function notation for the different transformations. So in function notation, how do you translate a graph left C? That's going to look like f of x plus c. That's function notation. The difference between what you see at the top and what you're seeing at the bottom is at the top we knew it was quadratic, so we had all the squares in our answers. Notice on this one we're just treating it in function notation, f of x. We could say what the parent function is, but we're just leaving it in function notation. And then translating right c would be f of x minus c. On both of those, we're affecting the x values, so we're keeping it in parentheses. C looks like the opposite of what it really is. when you want to translate a graph up C, then you want to affect not X, but Y. So Y in function notation is really just f of X. You want to add C on the back, not in parentheses, or subtract C, not in parentheses. That's going to be a vertical shift. Okay. Back in Algebra 2 and maybe Algebra 3, you used AHs and Ks. The letter doesn't really matter. So here in this pre-calc section, they're going to use all Cs. It doesn't matter if you like AH and K, you can change it. We will go back to AH and K at some point. Can I do anything to help you wake up?
Oh, I'm sorry.
Okay.
I'm awake. Just keep going.
Okay. Everybody's getting really distracted.
I'm so sorry.
Then they're distracting me with their facial expressions. It's okay. It's 6 hours and it's been a rainy day. I get it. Okay. So we'll go back to AH and K during chapter 2. Okay, so reflect the graph in the x-axis. That's the one that I think Logan did for us. You want to make what part negative, x or y? To reflect in the x-axis? I'm changing vertically, aren't I? So I'll be changing the y. Negative f of x, because f of x is y. If I'm reflecting in the y-axis, what part of the point is changing? The x, so this will be f of negative x. Okay, and to vertically stretch or shrink, we got that one. We take some scalar times our function, so c times f of x. Again, if you're doing a vertical stretch, you're affecting the y values, so you're doing it to all of f of x that's outside of the function notation, right? And you guys mentioned what values would make that stretch or shrink. You guys told me like numbers greater than 1 would be stretches, and numbers less than 1, but then we added greater than 0 would be shrinks. I'm adding the absolute values there because if the number in front of your function is negative, what will the negative do? It'll flip it. It has nothing to do with stretching and shrinking it. Okay, so that's something totally different. This one is stretch or shrink. Stretch. And then when it's between 0 and 1, that's going to be a shrink. Okay. Everybody okay so far? Okay, last one is the one that usually the first go round, maybe in Algebra 2, can kind of be confusing with horizontal shrink and stretch. Horizontal shrink and stretch works a lot like vertical, but instead of changing the y, we want to change the x's to horizontally stretch and shrink graphs. So we want to multiply our scalar inside with x, not the y on the outside. So that function notation is going to look like f of cx. It's going to have a similar set of rules in that you'll have a shrink or a stretch for those same intervals. C is greater than 1 or C is between 0 and 1. What happens for horizontal stretch and shrink? Jasmine?
It's the opposite of what it is for the vertical.
Yeah. So what it was for the vertical probably makes a lot of intuitive sense, right? When it's greater than 1, it stretches it. When it's less than 1, it shrinks it. And when you get to horizontal stretch and shrink, it's the opposite. So it's kind of like H, where left and right is the opposite of what you think it will be. So this is going to be a shrink when C is greater than 1. And this is going to be a stretch when C is between 0 and 1. Now, there is one little extra thing I'm going to add here in the notes for that horizontal stretch or shrink. If we describe horizontal stretch or shrink, like let's say I said, I want you to take a graph and I want you to horizontally stretch it by a factor of 2. I would still say stretch by a factor of 2. But what's the b value you would use in the function? The 1/2, the reciprocal, okay? So let's make a note to ourselves. use the reciprocal of stretch or shrink factor, or C. I'll move this up here in a second. Okay. So if you're putting it into a function, you have to remember to like change it to its reciprocal. If you see it in a function, like the absolute value of 1/3 x, you have to remember when you take that out, that's actually a stretch of 3. Even though it looks like a 1/3. So I always remember like everything that happens inside with that x, the h's, the left, right, and the horizontal stretch and shrinks, they're kind of the opposite of what I think they could be. All right, any questions on the yellow sheet? Okay, you can keep this handy because you might need it when we write a function notation. You want to have out your pink sheet in case you want to check on any of the parent graphs. And then I'm going to do some examples from section 1.7 so that you'll be prepped for your homework this evening. So we'll try to get through 2 examples today. If you're using like a binder system, you might want to put the yellow sheet in with your notes for 1.7 so you remember, okay, these are things I can study for function notation. If you're using the notebook and folders, you know, put that someplace where you know this is notes, not necessarily a worksheet. I might need to study these. Okay, so in 1.7, we're going to be talking about the parent functions and the transformations, which usually you guys are pretty good at because you spend a lot of time doing that in Algebra 2. So we just kind of need to like refresh our memory. Probably the things that I experience students having the most difficulties with in pre-calc will be stretches and shrinks. So you got to make sure your graph looks good. And when I ask you a graph on quizzes and tests, with transformations, that's going to be no calculator. So you can't just type it in and see it. You have to be able to figure it out. Okay. So here's an example. This is similar to the 4 things that you'll be asked to do on several of your homework assignment or homework problems tonight. Identify the parent function, describe your transformations, and sketch a graph. The last one, D, maybe is something you did less of in Algebra 2. Depends maybe who your teacher is, if they stress function notation or not. So I give you a function here. I'm going to let you and your group members work on A through C, which I think you should be able to do. And then if you get done, you can try D and see if you agree with our answer that we put on the board in a little bit. So I'll give you time to work on this, see if you're prepped for your homework tonight. If you've got questions, let me know. And talk to your group members.
All right. Oh, okay.
And there would also be a graph.
No, I think there was a reflection.
Okay, identify parent function. Y. Okay. It's square root by x.
sketch the graph. I describe transformation. It's wow. Horizontal, no, vertical stretching to flip the y-axis. Yeah. So it's going this way. Oh, right. By a factor of 2. So it's going right. How about we do 0? Wait, what does that equal? Or it doesn't exist in that.
No, see, when you stretch, because like you're, yeah, obviously how I was stretching is, I was literally stretching this way.
See how you're doing this way.
Wait,
Yeah.
So you guys are doing
0. Okay, what's a square root of 0 minus 3?
That's
Yours looks
That
horizontal.
doesn't work. That doesn't work. It has to be greater than 3. It has to be. Wait, no. It can be.
Well, that's why they're opposite, right? Okay, so like,
Yeah, and then it's just
But it can't be.
well, I always say like imagine your yourself in Photoshop.
We're so shy.
And then have you ever seen where your fingers pull at the top or bottom of the corner? What happens to your
0,
face
right?
if you
It's
just
just
pull
negative 2
down on
times
your
0.
picture?
There we go. Raise 0. So 4 square root of 1 is 1. You just negative 2 is
Yeah,
negative
because
2.
you stretch like
And then
really
that's
skinny
2
and long,
times negative 2.
right?
Wait,
So that's what a vertical
what's
stretch
square root
is.
of 2?
It would make
1
it
point
like
something.
taller.
Okay, so that is
And
0.
then what would a vertical shrink do?
Function
It
0.
would
Negative
make
2.2.
your face go like that and nowhere to go but out.
And then negative 6.
And then
It's vertically.
switch that around, think about
So
how long it's pulling it up and down. You're pulling it this way. As you stretch, you push back horizontally.
negative
And
3.46.
shrink, a horizontal shrink
So
will
it's-
make each step opposite.
Is you get flip-
We're both just big red.
Well, it is a
Alright,
vertical
no.
stretch. It is a vertical stretch.
I get
So
that.
I would treat it as
It's
a vertical
so
stretch.
stupid. Yeah.
Okay.
Why do you do
I'm keep doing this like that. I'm okay with that.
What does that mean?
There we go. There we go. We sketched the graph.
We
Okay.
use function notation.
What?
I'll sketch.
To right, I got that.
Yeah.
I didn't know about that one.
Function notation doesn't have a square root, it just has fx.
Mm.
So it's
Right,
literally
it's
gonna look
it's
like
It's
these
okay. Wait,
things
it's
all mashed
it's-
together with
it's
numbers.
it's
there's never
negative
gonna be
2
a
f. It's negative. It's negative 2.
No,
It's f
it's composition.
times. It's negative 2
It's
f
a reflection.
plus minus 3.
I mean, it's going down, right?
It's that, right? It's that.
Negative 2f x minus 1/2.
Okay, I'm gonna interrupt
I said that I'm not 600.
so that I can talk about graphing. I see lots of different strategies as I walk around the room. One of them being table of values, which really is fine. Note that if I'm asking you to graph this without a graphing calculator, you don't have a calculator to do your table of values. So you'd have to think wisely and choose values that you can take square roots of. But in Algebra 2, you were trying to move away from always having to create table of values. You wanted to understand characteristics of graphs so that you could graph them without making a table of values every single time. So would you all agree, this is my thought bubble right here, so just like imagine, that's what I'm thinking in my head. If I'm graphing a square root, that's the parent function for the square root. You have it on the library functions. And you should be able to pretty quickly like come up with those ordered pairs that work in the square root, right? 0, 0, 1, 1, 4, 2, because the square root of 4 is 2. So those are the first 3 points on the square root parent function. Are we okay with that? Okay. So if I'm graphing by transformations and not by table of values, this is what I would do. I'm thinking about in my head, maybe I'm going to reflect it, right? So like in my head, I'm not always writing this stuff down. In my head, I'm thinking about reflecting it. 0, 0, 1, negative 1, 4, negative 2, right? Okay, so here's 4, negative 2, here's 1, negative 1, here's 0, 0. Okay, so I got the reflection down. Then I'm thinking about in my head, maybe moving it right 3. Okay, so in my head, I can take that and I can move it right 3. 1, 2, 3. Okay, and where am I? 1, 2, 3, 4. Okay. So now I got these new points, right, that are going to be on that graph as I shift it right 3. Well, the last thing I have to do, and it doesn't really matter what order you do this, okay, but it's my vertical stretch. So if I'm vertically stretching it, I'm taking my y values and multiplying them by 2 in this case. I'm vertically stretching it by a factor of 2. So if your y value is 0 right here at 3, 0, your new point is also 3, 0, because 0 times 2 is 0. So I have a point at 3, 0, right there. This point would be 1, 2, 3, 4, negative 1. When I move that point right 3, it gets to 4. Okay. But I'm going to be stretching the y value. The y value was first down 1 or negative 1. When I multiply that by 2, I'm going to be going down 2. So my next point at 4 here, instead of going to 4, negative 1, I'm going to go to 4, negative 2. So you should have the point 4, negative 2 on your graph. And then if you wanted to do this other point out here, think about this point. This point used to be 4, negative 2. Then I shifted it right 3, so now it's at 7, negative 2. But I'm going to multiply my y value by 2, so it's really at 7, negative 4. So 1, 2, 3, 4, so that's 7, and then I'm going down 4. So here's 7, negative 4. So you maybe talked about, like in Algebra 2, like if you know in the square root graph that like normally from that like starting point to the first point, you normally go up 1, right 1. If you're vertically stretching it, then you know you're going to go up 2, right 1 to the first point. Right? You're just stretching that vertical movement by 2 or shrinking it by a half. And that'll do it for you. I will be checking on quizzes and tests that you have at least 2 accurate points. So you want to be able to figure out a way where you can stretch or shrink appropriately without calculators and get accurate points. You can always test them in a table of values or test them in the function if you need to. Okay, but that would be our graph. Let's see, we still have to do D, which is to write in function notation. So here's C. I'll put D right here. Okay, we want to write G, which is this function right here, in function notation. The important thing to remember when you're doing this on your homework, look at your yellow sheet, the bottom of the yellow sheet. That's all function notation. In function notation, there's no square roots, absolute values, squareds, anything like that. It's just f of x, right? So you really just want to take these transformations, like the negative 2, that's your reflection in your vertical stretch, and your x minus 3, that's your right 3, and put it into f of x. So that'll look like negative 2 f of x minus 3. That's function notation for your new function g of x. Okay. If I scroll back up to your parent function, if I write this down and then I tell you f of x is square root x, we know to apply those transformations to the square root function. But this is considered function notation. Okay, Josh.
So, I'm sorry, we're going back a little bit. How
Yes.
do you get the second point, the 4, negative 2?
Uh-huh.
Like, where does,
Well,
how do you
there's
plug
a-
that in?
Well, there's a couple ways. So, like, when I reflect, so, like, I know with the square root graph that, like, normally to get to my next point, I'll go up 1, right 1. When I reflect it, I will go down 1, right 1. But if I'm also vertically stretching, then vertically I have to go down 2, right 1.
Okay.
So I'm at 4, -2.
Okay.
So I use, like in Algebra 2, I use like the pattern of the parent graph. If you know your parent graph, you know how to like move horizontal and vertical stretches. The other thing was like I had moved it right 3, and then this point right here, if you kind of marked that at 1, -1, you at that point you're multiplying y by 2. So the new point is going to be at 1, -2.
Okay.
Alright. All right, there may be some also other questions. I think I just got just a minute left. We have to identify the parent function, state transformations, and write equations from the picture. Okay, what parent function do we have right here? Yes, quadratic, f of x equals x squared. What are my transformations?
Reflection in the x.
Reflect in x-axis. I heard left. Left 1.
Up.
And up 1. And apply those to write a new function for that. So that would be negative x plus 1 quantity squared plus 1.
Is it in that order though? I always forget where the.
I'm not really too particular about order. You should reflect before you do like vertical shifting in a graph, but I don't care what order you write them. It doesn't really matter. Unless you're reflecting in the y-axis, then you should just do reflections first. Okay.
So you were stuck with parentheses first, and so it's.
Reflections and all stretches and shrinks should be done before translations if you're graphing.
Okay.
I don't care what order you write them down on the paper if you're stating transformations. You do have a homework assignment.
I don't really.
I will see you tomorrow.